This is a video from section 12.5 and it's based off the lecture notes. In this video, we're going to look for the equation of a line L in 3 space. Let V be a vector that runs parallel to line L. Let P naught, which is equal to X naught, Y naught, Z naught, be a specific point on the line. Let P, which is equal to X, Y, Z, be an arbitrary point on the line. Let R naught and R be the position vectors of P naught and P, respectively. So let's circle back to the picture. So you can see here that I'm highlighting the specific point. This specific point is P naught. P is right here. Now, R naught is the position vector for P naught, which means the initial point is at the origin and the terminal point is at P naught. Okay? And so if I highlight it in blue, here's the position vector R naught. And then the position vector R is over here. The position vector R has an initial point at the origin and the terminal point is at P. Okay? And if you notice over here, I'll highlight V. V is a vector that runs parallel to the line. When you are finding the equation of a line in 2 space, you need a slope and a point. When you're finding the equation of a line in 3 space, you need a specific point on the line and you need a vector that runs parallel to the line. So by design, I have this vector here we call V that runs parallel to the line L. All right? Now, let's go back. A is going to be the vector that P naught P. So the initial point is P naught and the terminal point is P. So that's highlighted in red. Okay, so that's right here. So we have the vector A. Now, if you notice, if I take the position vector R, that's equal to R naught plus A. So that's just the triangle rule for adding vectors. And that's what I wrote down here. Next page. Since V and A run parallel, we can say that A is a scalar multiple of V. So in other words, A is equal to T times V. Now, remember that R is equal to R naught plus A. But I'm going to replace A with TV. So that says R is R naught plus TV. So what I'm going to do is I'm going to let V equal the vector ABC. Then TV is TA, TB, TC. So in other words, I'm just taking the scalar T and multiplying it by each component within vector V. And so R is the vector X, Y, Z. R naught is the vector X naught, Y naught, Z naught. And then we already know what TV is. It's the vector TA, TB, TC. And so X, Y, Z, that vector, is X naught, Y naught, Z naught, that vector, plus the vector TA, TB, TC. And this is the vector equation of the line L. In other words, it's the vector representation of that line. And so what I want to do next is I want to essentially equate components. And so when I do that, I get the following. X equals X naught plus AT. Y is equal to Y naught plus BT. Z is equal to Z naught plus CT. And this is where T can be any real number. So when that real number changes, your point on the line will inherently change, and you're going to end up capturing all the points along the line. Okay? Now, the above equations are called parametric equations, okay, of L through the point P naught and parallel to the vector V. Okay, so if you're given a specific point on the line and you're given a vector that runs parallel to the line, that is enough to be able to find the equation of the line. Now, what we want to do now is solve each of the parametric equations for t. So if x equals x naught plus at, if I solve for t, I get x minus x naught divided by a. So I just subtract x naught on both sides and divide both sides by a. Of course, a can't be 0, because if a is 0, that doesn't make any sense, right? And then if y equals y naught plus bt, and I solve for t, I get y minus y naught divided by b. And if z equals z naught plus ct, then t equals z minus z naught divided by c. And in a similar argument, b and c can't be 0 either. And so if t equals x minus x naught over a, and t equals y minus y naught over b, and t equals z minus z naught over c, it would naturally follow that x minus x naught over a equals y minus y naught over b equals z minus z naught over c. And again, I want to stress that a, b, and c cannot be 0. These equations are called the symmetric equations of the line. So it's just another way to express the line. The numbers a, b, and c are called the direction numbers, okay, of the line L. Let's take a look at an example. So this example says, find vector and parametric equations for the given line. And this is the line through the point 0, 14, negative 10, and parallel to the line L. And this line is given by x equals negative 1 plus 2t, y equals 6 minus 3t, and z equals 3 plus 9t. Now, what do we need to find the equation of a line? We need a specific point on the line. Well, we got that. It's 0, 14, negative 10. And we need a vector that runs parallel to the line. Now, what's going on there? So to get the vector, what we need is we're going to read off the coefficients of t. So notice here, this 2 will be my a, negative 3 will be my b, and 9 will be my c. And so the vector 2, negative 3, 9 is a vector that runs parallel to the line x equals negative 1 plus 2t, y equals 6 minus 3t, z equals 3 plus 9t. Okay? So if it runs parallel to that line, it's going to run parallel to the line I want. And that's basically what I say on the next page. So v equals 2, negative 3, 9, so that vector runs parallel. I should spell parallel, right? Parallel. So this vector v runs parallel to the line that I desire. So now, given the point P naught, which is 0, 14, negative 10, and the vector v, which is 2, negative 3, 9, we have the given vector equation. So x, y, z, I'm just going to leave this scalar out, by the way. So the vector x, y, z is equal to the position vector of the point P naught. And so the position vector is 0, 14, negative 10, plus t times the vector v, which in this case is 2, negative 3, 9. So that's the vector equation. And so what I want to do from there is basically equate components. And that's going to give us the parametric equations for the line. And so over here, the parametric equations are x equals 0 plus 2t, y equals 14 minus 3t, and z equals negative 10 plus 9t, where t is any real number. So I'm thinking in terms of point plus scalar multiple of vector. So that's the idea. And this is how you find an equation of a line in 3-space. We are going to do more examples in the next video, but again, this is a video from section 12.5 and it's based off the lecture notes, and this would be part 1. All right, thank you.